It says, find the volume of the solid obtained by rotating the region bounded by y equal to the cube root of x and y equal to x cubed. And then we have 3 different axes over here. So why don't we graph the situation? Sorry, I know he went over A, but let's just review it together. So we got a set of axes over here like this. And why don't we graph our x cubed? So we know we're gonna have a 0, 0 here. Maybe this is gonna be like 1, 1. And then we're gonna have a -1 here and a -1 here. Okay. So why don't we graph our x cubed graph? Our x cubed graph looks something like this. Comes up like this. And comes down like this. Right? And then when we look at the cube root of x, the cube root of x looks like this. It comes like this guy. This is y equal to x cubed, and this is y equal to the cube root of x. Is there any questions about this graph? So far, I mean. Now, the sub told me that he did go over part A, and he said that Dwayne, I know Dwayne, he's a funny guy to me, and he told me that he had asked, do you guys only want to rotate the region by part in quadrant 1, or did you want to rotate the whole thing? And he told me that like only one person responded, which, you know, surprise level 0, right? I mean, you guys are the world's best poker players. So then I spent some time trying to guess who it was that actually voted. Was it you, Ken? Ken, were you the one that voted, or was it someone else? I'm just curious. It's Linda. I lost the bet, man. All right, Linda. Linda, thank you. So I'm gonna reproduce this graph 3 times because it's probably gonna do 3 separate problems. Set it up 3 different ways. So let's do this. Paste here. Let's do one more down here. Paste this guy. Okay. We're gonna rotate first about the y-axis. So we're going this way. So I know he already did part A with you, but let's just look at it again together. So this is how I would think about it. Step 1, chop up perpendicular to the axis of rotation. For us, the axis of rotation is the y-axis. Perpendicular means you're going to get horizontal lines. So it looks like this. Any questions? Step 2, dx or dy. You already went over this, so maybe I won't try to get you to answer. But the way that I think about it is, this is one little disk there. And when you think about it, that little bit of thickness lies on the y-axis. So this means that it's going to be a dy. Is there any questions about that second step there? No. Next question is, we got to set it up. And in order to set it up, we have to also think about if it's going to be discs or washers. So how can I tell? How can I tell if it's a disc or a washer? Well, if you think about taking this red part here and rotating it around the axis, you're going to have a hole right there. You're going to have a hole right here. So it's definitely going to be a washer. What's interesting about this problem, though, is it's almost like you have two pieces. You're rotating this piece around, but you're also rotating this piece around, right? So why don't we treat each piece separately? Let's first work with this piece, and then we'll worry about this piece next. Does that make sense? So when we do that first piece over there, we got to look and we know that it's going to be a dy thing. But we want to know for this first piece, what is the smallest y can be and what is the biggest that y can be. And when I look at, so I'm working with this shaded region right here. I'm going to shade it in yellow. This yellow region is the part that I'm rotating around. And I know I'm doing a dy integral, so I'm looking to see in that shaded region what's the smallest and biggest y can be. And to me, it looks like the smallest y can be a 0 and the biggest y can be is 1. And I know I have a washer situation, so this is going to be pi r big squared minus pi r small squared, right? And I'm going to replace what r big and r small are in a second. Now, let me pause here for a second. Is there any questions so far? No question. All right. Now, I hope we can all see that r big should be the blue curve and r small should be the green curve, right? Because you're going out to the green curve for the small radius, going out to the blue curve for the big radius. So why don't I, when I come over here, why don't I change this to green to make it obvious? Okay. But really for us, we need to write all of our functions in terms of y, whereas these functions are written in terms of x. So how do I write this guy in terms of y? Well, what I can do is I can just take the cube root of both sides or raise, exponentiate each side by 1/3. So then you're going to get x is equal to y to the 1/3 power. We'll write that in right here. Y to the 1/3. And then for the green one, I want to do the same thing, but the opposite. I need to cube both sides. So in this case, this guy becomes x is equal to y cubed. And then that's going to be your r small. Does that make sense for everybody? Now that's just that first yellow chunk there. Any questions? Let's now find that orange chunk. If I find the orange chunk over here, I hope you can see we have the same scenario. We're still going to integrate. It's still going to be a dy type thing because the little bit of thickness lies on the y. A student asks, why is the green graph the small one? So when you look at this, the small radius goes from the axis of rotation to the first graph. And can you see how the first graph that I hit is the green one? And the big radius is going to be the distance from the axis of rotation to the second, the the graph that's further to the right, and the blue graph is further to the right. So that should be the big one. Does that make sense? Right. So the student says, oh, I see. I was looking at from the X. So this is why I teach it this way, to be honest. Like, you got to figure out if it's a dy situation or a dx situation. And when you're in a dy situation, that means you're looking at it as a dy is a left right. Whereas dx would be up down. So I try to always explain it like in these 3 steps. First, chop it up, then figure out your variable of integration, and that's going to tell you if it's left, right, or up, down. Okay, cool. When we look at this orange region, what's the smallest that y could be, and what's the biggest that y could be? The smallest that y could be is -1. And the biggest that y could be is 0. And in this case, man, I didn't have to split it up. I just realized. Anyways, in this case, our big is still the blue graph. So then I could just go from pi y to the 1/3 power squared. And the small radius is still the green graph. So I can write this as a y cubed squared. So it was unnecessary to split this into 2 integrals. I could have just gone from -1 to 0. I was thinking maybe it would flip at some point, but it didn't. Does that make sense to everybody? This is the one that he went over, so hopefully you got the same answer. Let's take a look at about x equal to -1. This situation is a little bit trickier. So let's come over here. Let me lower this a little bit. Maybe I could have just reduced the size of this a little bit. Or I guess I could do both. Okay. So this one was x equal to -1. X equal to -1 is like this. Something like that. And we want to chop up perpendicular to the axis of rotation. So the axis of rotation is parallel to the y-axis. So we chop it up this way. Right. A student just mentioned that the sub just took this guy and multiplied it by 2. I was going to make a comment about that, and then I forgot. But yeah, you can do that because when you rotate it around, you're going to get this, you're going to get an object that's symmetric above the x-axis and below the x-axis. So those 2 volumes are going to be the same. So you could just multiply it like that. That for sure works. I'm just doing it more mechanically so we get practice. So I hope it's obvious to you guys. So I'm just going to write out the steps again. We chop up perpendicular to the axis of rotation. We just did that. The second question is it dx or dy? In this case, it's dy again. The third thing you want to do is you want to set it up So unfortunately, in this scenario, I am going to have to split it up into two pieces. And I think that'll become clearer when we do it. But I'm going to look at the yellow piece again first. So for this piece right here, we're going to go from 0 to 1 because in that yellow region, the smallest y value we have is 0, and the biggest y value we have is 1. I guess I had assumed that you realized that it was a dy integral. We wanted to do pi r big squared plus pi r small squared, right? So what do you guys think r big should be? I guess since we already did this before, I can rewrite this guy as x equal to, oops. I could write this guy as x equal to y to the 1/3 power. And then the green graph would be x equal to y cubed. So you know what? Maybe I should move it down here so it's right near the thing. All right. So when we say x equal to y cubed, they're saying that that's the distance from here to here. So if I were to shade in a disk, let's say we're working with this disk right here. I know that the distance from here to here is the x value, which is y to the 1/3 power. But my radius, my r big, should be the distance from here to here. So what do you guys think r big is going to be? Any thoughts? Student that just anonymously answered me privately, not anonymously, but privately. I think you just found r small. I'm looking for r big here. So one more time, the distance from here to here is x, which is y to the 1/3. What is the entire distance here? It would be, this is how I think about it. I think of this as the distance from here to here is y to the 1/3 power. But then I have this extra distance from here to here. That extra distance from here to here is 1. So it'll be y to the 1/3 plus 1. Another way you could think of it, that's sort of thinking about it more visually. You could think about it as well like this. If this, you think of this as x equal to negative, sorry, yeah, x equal to -1. You could also think of this as y to the 1/3 minus -1. In other words, you subtract this curve from this curve, and then that would give you that whole length there. Does that make sense to everybody? So I have a question from a student. Why is r big and r small added here when the other was subtracted again? I guess if you're talking about this was subtracted right here, I haven't even filled in that part yet. So, but this part here is a typo. So if you're asking me about this, that for sure is a subtraction. So it's still area of a big circle minus area of the small circle. Does that make sense? That was just a blunder. I'm not sure if you're asking about this part or this part. So I fixed this part. This is for sure subtraction. I hope you're not asking about this, but in case you were okay, in case you were asking about this, again, the distance from here to here is y to the 1/3 power, and the distance from here to here is 1. So that total distance would be y to the 1/3 plus 1. That's one way to think about it. The other way to think about it is, okay, what's the x value for this curve? It's this. What's the x value for this curve? It's this. You could subtract those two x values, and that would give you the length. Y to the 1/3 minus -1 is this. What do you guys think the answer should be for this one? R small. Dots. If you just said y to the 1/3 power, that's just the distance from here to here. Y cubed, sorry, that's just the distance from here to here. But our radius, we're not rotating about the y-axis anymore, we're rotating about the x minus 1. So we want this whole distance from here to here. So you can either think of it as y cubed plus 1, or you could think of it as the big function, which is y cubed, minus the smaller function, which is -1. So either way. Does that make sense? That's right, Ken. Good job. Now this is just part of it. We still need to do the second part. So this is where I meant to put the plus. And then we want to do the same thing. But now we want to work with this orange area here. And we're still going to have that little bit of thickness right there like this. So my question for you is, well, first we need to find the smallest y value. The smallest y value is -1. The smallest, the largest y value on that orange region is 0. But this time, I think the role of R big and R small changes. I almost did it again, shoot. So how are we going to find the distance from here to here? Does anybody have a any feeling? What would R big be in this case? Just y cubed is one answer. Oops. So if you put in a y cubed, actually, your distance would be from here to here. Right? Because y cubed is the x value. So you're going to get well, it's going to be a negative number. Y to the 1/3, y to the 1/3 right here. That's going to be the distance from here to here. And that's going to be the, that's also going to give you a negative number. But I almost feel like that's what it would be if I was rotating about the y-axis, but I'm rotating about this axis. So I think the easiest way to think about this is to think about taking the green curve, which is clearly R big. I hope you can see that, and subtract it, finding the distance from here to here. And I can find that by just subtracting the two functions, right? So, so we can think of this as this function, which is the green one, which is y cubed, minus the second function, which is x to the -1. And if you think about it for a second, this kind of makes sense because our y cubed here is going to be a negative number. And you're going to add 1 to that. So you're going to take a negative number and add 1, you get this distance that's smaller than 1. And the distance from the green curve to the dotted red line is definitely smaller than 1. So that kind of makes sense. Okay. Then for the other one, we're going to have I hope you guys can see that R small is going to be the distance from the blue curve to -1. So the blue curve is given by the cube root of y. So this should be the cube root of y. And we want to subtract the two functions. In other words, if I want the distance from here to here, I just subtract the x values. So I take the bigger x value, which is the one on the right, and subtract away the smaller x value, which is the one on the left. So this will be minus -1. And this would be the setup for this particular volume. So now that we've gone over this, I feel like if the question is in the first quadrant, it's easy to visualize. You can think of, oh, I just add 1. But when it's in the fourth quadrant over here, it's probably more convenient to subtract away the right x value from the left x value. So let me make a note here. We are subtracting the right x value from the left x value. Okay. All right, cool. You know, if you feel like this is quite difficult, you're not the only ones. Every semester, the topics students struggle with the most are the word problems and the volume questions. So, and curve sketching is sort of like fourth place. But that's why I moved to the end of the course, to give us time to master the basics. And that's why I have those topics as if you want an A, you gotta master those topics, those standards. It's already 10:51. I think it was worth talking about this. Do I want to do the last one? Or do you want to take a break? I leave it up to you. You want to take a break now or you want to do the last one? Yes, I could do the last one. Let's do the last one. The last one's about x equal to 3. I'll try to do a little bit faster because my main topic today is to talk about the shells. But okay, so this is x equal to 3. So I guess the first thing we're going to do is we're going to chop up perpendicular to axis of rotation. So in this case, it's going to be and then the second core thing is dx or dy. To me, it's dy, right? And then I guess a natural question to ask is, do we need to split it into 2 pieces or can I do it all at once? And how do I know? The answer to that question is, if the idea of like the right function and the left function, if those guys are a little bit confusing, if it switches, right? Like here, the inside guy is blue, and then it switches to outside, then we want to, then we need to split it into two pieces. It's like the curves that cross. When the curves that cross more than once, the role of the top function, the bottom function changes, or the role of the left function and the right function changes. So in this case, we're going to have to split into two pieces. The first piece is going to be those y values that go from 0 to 1. And then we're going to add the result we get for the second piece that goes from -1 to 0. Does that make sense? All right. Next, I want to know, I know that it's going to be pi r big squared plus, minus pi r small squared. R big will be the distance from here to here. I really should have relabeled these guys a long time ago. This guy is, the blue graph is x equal to y to the 1/3 power, and the green graph was x equal to y cubed. So if I want R big is the distance from the red to the green. So we're going to go 3, which is the right x value, minus y cubed, which is the left x value. That's going to be R big. So R big is the distance from here to here. Does that make sense? Then R small would be the distance from the red line to the blue curve. And that red line is 3. And that blue curve is y to the 1/3. We want to do the same thing for this next one. But the roles of big and small get interchanged. So R big in this case is going to be the distance from the red line to the blue curve. So that's going to be 3 minus whatever the blue curve is. The blue curve is y to the 1/3 power. And R small is going to be the distance from the red line to the green curve. The red curve is 3, and the green curve is y cubed. Some of you might be bothered by the fact that this is a minus, but it's supposed to somehow be R big. I just want to remind you that this x value is negative. So you're actually, in the end, going to be adding. Okay. One student asks, could you do y cubed minus 3? In this particular case, you could actually, because you're squaring, so it doesn't really matter which order you subtract them in. But ideologically, I think of the distance as being the difference between the two x values, and I would subtract the right x value from the left x value, because the numbers on the right are bigger than the numbers on the left, and we expect radiuses to be a positive number.